Hello and welcome to another video. In this video we're going to be going over the problems from the Biweekly Contest 130, and I did the weekly contest already. I think this one, the first three problems are pretty easy. The fourth one though is I think very hard, and so that one took me a while, so I did the other contest first. I think that one was a little bit more straightforward. Okay, so in this one, so the first problem is check that the grid satisfies conditions. So basically they tell you that grid has to be like this. Every column, all the numbers have to be the same down the column, and then every row the numbers can't be the same. So like in any two adjacent items, they can't be the same. So this is pretty easy. All I did was I just went through the first row and I just checked here, are all my columns different? So all these are different, and then you just go down every column. So instead of traversing down rows, you just go down every column and you make sure for that whole column, are all the numbers the same? So you check, are all these different first? Like, are all adjacent ones different? And then you go down every column and you just check, are all the numbers the same in that column? So that one, not too much to do. Yeah. And let's go to the next one. So this one was kind of cool, actually. So in this one, you basically have to recognize, so in this one they said you have a 2D array points and a string s where points I represents the coordinates of point and si represents the tag. Valid square is a square center at 0, 0 that has edges parallel to the axis and does not contain 2 points with the same tag. Return the maximum number of points. And so the point is in the square if it lies on or within the square. The side length can be 0. So essentially, let's actually just make the square a little bit bigger. So your square is going to grow out. Maybe I actually want to take a picture here. So let's just make this. Yeah. So let's take this square and let's actually just draw it. So it's going to use it here, but let's do it here. So here's our square. So essentially, your square is going to grow out like every point is on a can't be between like anything, right? Like the points are numbers. So every point has to be on one of these like cross sections, like here or here or here or whatever. And so knowing that, your square is going to start here and it's going to grow out like one at a time. So it'll grow out 1 in every direction, then 2 in every direction, then 3 in every direction, and so on and so on and so on. So it'll grow out every direction equally, which means that when your points, it doesn't really matter like if your points are negative or positive value or whatever. Because like let's say you have a point here, like this point is or actually let's see, so let's say you have this point actually, so this is -1, -2, it's right over here. So that would be the same as having a point here or here or here. Like it doesn't really matter because a square is going to grow out the same in every direction and will capture that point. So the negative or positive or whatever, like if it's here or here or here or here, as long as it's the same distance away from like the center, you can kind of, it doesn't really matter. So the same one here, this is 3 and 3, so it could be like 3 and 3 this way or 3 and 3 this way. Like a 3 by 3 square will cover all of these, and so on and so on and so on. So if a point's here, it's the same as like you just move it across the axis. It'd be the same as here, or the same as here, the same as here, and so on. So basically the only thing you need to know is figure out like what information do I actually need to know to capture a point. And so you capture a point, and you can recognize this by when your square gets to the bigger of the two values for this coordinate. So essentially like here, whenever my square is length 3, like whenever my square is a 3 by 3, it will cover this point. Then whenever my square is a 4 by 4, it'll cover this point. So I could have a point that's like 1 infinity, let's say, which would be like here. And then, or not infinity, let's say 1,000,000, right? And then when my square is 1,000,000, then it will cover this point. So the smaller value doesn't matter of the coordinate. All you really care about is the bigger value of the coordinate. And all you care about is, like I said, positive or negative doesn't matter. So now that you know that your square will capture point when side length, or not side length, when like the, yeah, I guess side length. Actually, will it be side length? No, it won't be side length, but when it grows, like when it grows, like it'll basically capture points in the order. So maybe I won't say when, in the order of the maximum of x and y, and this is the absolute value. So you can basically just sort your points. So this is what I did. So you can just sort your points. You just take the bigger of the two coordinates. So like you just say like, okay, if my coordinate is 3, -3, I'll take the bigger one, obviously here, and you take the absolute value of both, so obviously here's 3 and 3, doesn't matter. But let's say, like I said, your coordinate's 1 and 1,000,000, you would just say like, okay, well my square will get here at 1,000,000. You know, I don't really care about the side length actually, I'll just say like anything, so anything with a side length of, like anything with a big side length of less than 1,000,000, I can include in my square without including this guy. So if I have something like 1,000,000 minus 1 and 1,000,000 minus 1, positive or negative, so 1,000,000 minus 1, 1,000,000 minus 1, then I can capture this point before this point. So that's how you can sort your points. You just sort your points and just take the bigger of the two values, take the absolute values, and then also put in, so the other thing is they can't have the same tag, so every point has a tag. So I just made a new array, and I just said my array is going to be my bigger of the two coordinate values, the absolute value of it, and the tag. And then I'm going to sort it. And then I'm going to have a visited set. And then basically what you do, so I'm just going to have like an array of numbers. Like, so let's see. Let's just make an array of numbers here. So let's say we have an array of numbers, and these will be so it'll be a number and a tag. So let's say we have like 1A here, 2A, or 2A, or let's say 2B, and then we have like 3B, or 3C, and then we have like 5D, 5, so this will be a fine example. Okay, so let's say we have this. So basically what we do is we start at the first point, and we say like, okay, so we know that if we have it sorted, we have to check our points in groups. So if we're at a 1 here, we have to get all the points that have a 1 because they're going to be captured at the same time. So in this case, we only have 1, which means we can actually capture this point in like the smallest square we can. So this would be fine to add to the square. And then we're going to have a visited set. So we're going to say, okay, tag A has been visited. And I think they tell you that you can't have the same tag multiple times, I believe. Yeah, it does not contain the same points. So you're going to say, okay, I can take this point and I visited A. Now I go over here and I say, okay, I start again. So I have a side length of 2, or like whatever, distance of 2. So if there were any more points with distance of 2, they would all be captured in that square. So in order to capture this one, I have to capture every single distance of 2 that I can. So if there's a tag A in this 2, then I can't do it. In this case, there's only 1, so I can. And then I'll say B is visited. And then we go to 3 and we check again. Do we have anything else with the 3? No, we don't. We just have this one, so we can capture it and see. And now here, with this distance of 5, we actually have 2 points. So these 2 points are going to be reached at the same time. So in order to get one of them, like we basically have to get either this whole group or nothing. And we can't take the whole group because A has already been visited. So essentially what you do is you sort your points, and at whatever number you get to, you check like how many different tags are there of that number in your sorted array. And then you either take all of them or nothing. And if you take nothing, then you're basically done, because anything bigger than that will have captured these as well. So you can't do that. So in this case, we can capture a 1, 2, 3, and then we can't get these 2 because there's already an A. So we just return 3. So that's kind of the idea here, is you take all of these, you just take the bigger of the two values, take the absolute value, as well as the tag, and you capture them in groups. So that's kind of what I did here. So you sort your points and give them the tag, and then you have a result in the visited set. And then I just say like, okay, my current point is this point, and I'm going to get every single point with that number. And if any one of those is invisited, I'm done. I can't do anything there. Otherwise, I'm going to keep adding to like my group length, and then if I was able to go through my entire group and nothing was tagged before, then I'm just going to add the entire group. And then I'll move on to the next group and the next group and the next group. And it's pretty easy because it's sorted, so your group is just all the points with the same number. So this was kind of difficult, like figuring out, like when I first read it, I thought it was going to be very complicated, but then you realize the square grows the same distance in every direction. So like a lot of this is one of those problems that's like, can you take a bunch of useless information and figure out what you need to make the problem pretty easy? Okay. So this one, so you have a string and you want to partition it into one or more balance substrings. And for these balance substrings, every character occurs with the same frequency. So you would do something like this. And then basically you want to partition it into as few, I believe, as minimum bound substrings that you can. And about substring, and they tell you what it is. So this is and also, so let's go through some of these examples, I guess. So this one, you can partition into FAB, and then this, and this. Because C's and D's occur more than once and right next to each other, you can't, like, there's no other way to do it. Well, you can do other stuff, but it's going to be worse. Like, you can take FABC as one, and then the C would have to be or you can take, like, FABC, maybe, like, CD, and then this would be one, so there would be three. So I guess there's a few ways to do it. And they kind of show you that. And then there's this one. So this one, you can partition it into two. So one, you have ABAB, and then the other one is this. And there's 1,000 characters in the string. So this one's a kind of straightforward sort of DP problem, I'd say. So basically what you do here is you start at some index. So let's say we start at like the first index in the string. And we basically keep track of the letter counts of every single letter in our string. So let's actually go through that as well. So let's say our string is like, and I'll just show you the DP for like the first iteration. So let's say our string is actually this one. So let's take this, put it into an array. So A, B, A, B, A, B, A, C, C, D. Let's just actually cut it here, I think. Actually, we can do the rest of it. It's fine. Yeah, because it's pretty fast. So C, C, D. So we need two more. So D, B. This is 10. Okay. So essentially, let's just say we start here, and this is going to be the same thing for every single DP. So basically, we just, for a current index, first of all, if we're done, like if we're at the end, we can just return 0, like standard DP. But the rest of it is, we can't really like say whether to take this letter or not take this letter, because we have to know like too much information, and our constraints are small enough that we can, instead of figuring out like do we just take a letter or not take a letter, we can just start at an index and just choose all valid split options. And so I'll kind of show you what I mean by that. So essentially, we are going to have a dictionary of letter counts. So we have A's, B's, C's, and D's that we're going to make in our DP, which is fine because there's only 26 characters. So that's totally fine. And we're basically going to say, like, okay, for this character, if we have this A, and we just only take this A, then what would happen here is we can't split it like this. Like we can't split like this, because not every single letter has the same. Well, actually, sorry. In this case, we can. Every single letter does have the same count because these don't exist. So you can actually do it. And the way to actually efficiently keep track of the max letter count is pretty easy. You can just so basically what you can do is you can set an initial max letter count to 0. And then whenever your character count of a letter becomes more than that, then you just change your max letter count and you say, okay, I have one letter with that max letter count. And then if I have any more letters that reach that count, then I add to that number. And if I have a letter that gets over the max letter count, then I reset the number of letters to 1 again, and I change the max letter count. And then whenever you check, can I recurse? You just check like, okay, how many letters with max letter count do I have? And this has to be the length of your dictionary, right? Because every single letter has to have the same letter count. So in this case, we would have only one letter with this letter count, and so we can't actually recurse. So we can say like, okay, well, maybe we'll stop here, and we'll just recurse, and our next iteration will start here, and then we'll just do one string plus starting here. We could do that. Or we could keep going. So in this case, we'll add 1b. And can we recurse here? Yes, because every single letter has the same count, so we could recurse here as well. Or we could keep going, and you can basically keep going. So like in this case, you can't recurse because your max letter count is 2, and you only have one letter with that count, but you have 2 letters total. So here we can recurse again, and then here we can't, and here we can again. And the constraints are small enough that basically you can have like a loop in your DP, and then all you need is the index, so it'll be n² solution, which is fine. So here we can't, here we can't, Let's see if we can anymore, actually. I don't think we ever can anymore. So let's actually go back and actually look at another important situation. So let's say we recurse here, right? And we don't know, let's say we recurse, we'll say like, okay, this will be our first part, and then we'll just recurse, and we'll start over here. So now, if we chose to do this, and this is a good example, we're going to have cases where no matter what we do, actually, no, I don't think we're going to have cases no matter what we do, we're going to have an invalid, because we can always just take one letter, I think. So even though I had that in my code, I'm looking at it, and I don't think there's any way where you can't split it up. Because even though you only have one A, you can just say, like, I'll just split it up into this, right? So actually, you won't have cases where you can't split at all. So what we could do is we could split it like this, and now, but we'd have to split like this, right? But we'd have to split like, yeah. So essentially, when we recurse, we're gonna say, okay, we can split on here, but if we keep going, we're never gonna be able to split again because the letter counts will never match after that. But that's kind of basically the idea. Is you just loop through your word and you just check, can I recurse, can I recurse, can I recurse, and you get the minimum of those. Yeah, so let's take a look at the code. So it's pretty straightforward. So you have a basic DP. If you're out of bounds, return 0. Have a counts dictionary of letters. Have a max count and a count, like I said. So the count is just the count of letters that have the max count. Initialize your result to infinity, and then you just loop through. So you just say, for my current letter, increase its count. If the count is bigger than max count, then make max count equal to that. You could alternatively, like every single time, check is all the count of every letter is the same, but that's going to be a little bit slower. That's like O of 26, where this is O1. So it'll still probably pass, but yeah. Anyway, and then you basically just check. If all my letters have the same count, then I can recurse. So if I recurse, it'll just be one substring plus DP of the index to where it recurs. So pretty straightforward. And yeah, maybe you can do some faster stuff, but okay, so this is a really hard one, and I should have an explanation for this. Honestly, it takes a while to even figure out what they're talking about, but there's a lot here. So let's get rid of all this. Okay. So here, you have a powerful array for an integer, which is the shortest sorted array of powers of 2 that sum up to x. So this is one way of thinking about it, but another way of thinking about it is a powerful array is basically, for a number, where are all the 1 bits for the number, and just like print those numbers in ascending order. So for example, for 11, the 1 bits are here. So this is 1, this is 2, and this is 8. And so for 11, it would just be 1, 2, 8, and so on. So where are all the 1 bits set, and just sort them in ascending order. And so the array bignums is created by concatenating powerful arrays for every positive integer in ascending order. So essentially, for 1, you would just have a 1. For 2, you would just have a 2. For 3, you would have 1, 2. For 4, you would have 4. For 5, you would have 1, 4. For 6, you would have 2, 4. For 7, you have 1, 2, 4, and so on. You're given queries, where queries are from to mod, where you should calculate big nums. So you're basically saying get the product of all the big nums, get all the values in big nums from the start to the end of the query, modded by mod. So in this example, this took me a while to figure out what's going on, but essentially, so this query is 137 actually means give me the numbers from big nums index 1 to index 3 multiplied by each other, modded by 7. So you get 2 times 1 times 2, modded by 7, which is 4. In the second example, so they have 2 queries. So 2 to 5 is here, to here. So this is just 8 modded by 3, which is 2. And then 7 is 1, 2, 3, 4, 5, 6, 7. So that's just 2 modded by 4, which is 2. Okay. So basically, you can't do this, and you can actually look. The constraints are too big to actually make out this big nums array, because the big nums array can be up to 10 to the 15th. So obviously, you can't just like make it and then do the query, because that wouldn't be a hard problem anyway. So you have to figure out a way to do this more efficiently, and pretty much always you're gonna have to do some kind of like bit thing, or I mean, in this you can kind of realize you have to do some kind of bit thing, because you're basically getting powers of 2, And you realize you can't make big nums, but you have to do some kind of optimization to get these things. And so there's kind of like two parts you need for this problem to solve it. So one part, like let's just focus, first of all, when they say get query 1 through, so they want to get the product of all the numbers from 1 through 3. Let's get that part out of the way. Like let's say they want to get the product of all the numbers from X to Y modded by whatever. We won't even include the mod because that doesn't really matter. Like the mod, you just get it and you mod it. Nothing there. So instead of this, what you can do is you can actually get the product of X to Y, not X to Y. You can get the product of 0 to X minus 1. And then you can get the product of 0 to Y. And then you can basically say, give me this. So, okay, for some reason I can't cut it, but okay. Maybe I can do it like this. Hopefully. Okay, there we go. Okay, so this is basically that. Because if you have a product of like A, B, C, D, E, F, G, and so on, right? And I want the product of just this section here. That's the same as this whole thing divided by this, right? Like that's the same as if I want EFG. That's the same thing as this whole thing divided by A, B, C, D. For some reason I wrote this twice. Okay, like this, right? Because basically this just cancels. So instead of like doing the subquery part, we can just do two queries. We can do one query of 0 to Y, then we can do another query of 0 to X minus 1, and we can just divide. And in fact, we're not even going to need, as you're going to see, we're not even going to need to do like the product. We're going to calculate something else, but it's going to be kind of the same thing. So that takes care of like that. So now basically, if we know how to do a query of 0 to some value, then we can kind of solve the problem. So if we can do a 0 to X, we can solve this problem. But still same thing. It's way too big to just like do manually. So basically, we have to try to figure out a couple things. So if we can figure out for a given integer X, how many values are in big nums for X, right? So for example, if we say our integer is 3, then big nums would look like, well, we would need to fill out 1 through 3, right? So 1, 2, and then this would be 3. So in this case, we have 4 values in big nums for 3, right? Similarly, if we have 6, it would be like 1, 2, 3, and then we have 4, and then we have 5. So 5 would be like this, and 6 would be like this. So if for 6, we would have, let's see, 4, 6, 9 values. Yeah. So if we could figure that out, then we can kind of say, okay, let's get the biggest integer that fits in the query, right? So if our query is like 0 to 10, that means we have 11. That means our array that we're working with, our subarray, is 11 numbers. So we're basically looking for the biggest number that when you make big nums for it is 11 or less. And if we can figure that out, then we might have some remainder. Like for example, like let's look at this. So let's say we have 0 to 10 here. We're looking 0 to 10. So 0 to 10 in big nums would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you can see the numbers this represents is actually, so 1, 2, 3, 4, 5, 6, and then 7 doesn't quite fit, right? You can see we have most of the 7, but we don't. So for 6, for the number 6, so this 0 to 10, by the way, is 11 indices, right? So we're basically saying, like, what's the biggest number that will fit in 11 indices? So 6 will actually fit in 1, 2, 3, 4, 5, 6, 7, 8, 9 indices, right? Like 6 will take up 9 slots in the big nums array. And then we have 2 leftover slots. And once we have, and if we get our number, so if we get this biggest integer that fits in our query and remaining elements left to fill, then we can kind of like figure out what the next number is. That part we can do pretty quickly, right? Because like, let's say we have some number like 6, and then we know our biggest number 7 that we couldn't put in there, and we have 2 elements left. Then we could just be like, okay, what's the binary for 7? So 7 would be 4 like this. And then we know that the bits of 7 are inserted from smallest to biggest. So we could say like, okay, well, we know 7 doesn't quite fit. So let's just take all the bits from 7, only 2 bits from 7, and let's use those 2 bits as well. So we'll have 1 and 2. So we'll have whatever the result was for 6, and then we'll have 1 and 2 from 7. So that's the first part you need to solve this problem, is basically given a number, how many slots does it take up, and then you can binary search for the biggest number that fits and the remainder. And that will take care of like getting the number. But then you need to figure out how to do the product, right? So if I say like, okay, well, 6 is the biggest number that fits, but how do I get the product of 1 to 6 or some range, right? 1 to whatever number I got. So this, oh, and by the way, so both of these things are going to be very similar. So let's actually look through how to figure out what's the biggest number that fits, first of all. So instead of what's the biggest number that fits, we're going to just say, like, given a number, how many digits does that take up? And then we can just binary search for that to figure out what biggest number it fits. So for example, if we have, so ignore this whole BCD thing. This is like irrelevant. So let's look at the binary and let's look at some patterns. And this is kind of good. So if we had 6, basically recognize that everything in big nums is just a power of 2. So for example, 6, the first number is this 1 for 1, then the second number is this 2, then we have the 1 for 3, then this, then this, then this, and this, and this. Right, so you have 1, 2, 3, 4, 5, 6, 7, 8, 9, I believe. Yeah, so you have 9. So if you said 6, every single one of these bits is a slot in big nums. So that's why we figured out that 6 took up 9. So if we could somehow figure out for a number, how many bits are in every number up until that number, that's the answer of how many slots does it take up in big nums. And you can actually figure this out in probably different ways, but this is kind of how I did it. So you can kind of find a pattern here. So if you actually look at like 1 bit at a time, you can notice that the 0 bit, like 2 to the 0, flips every single bit, right? So it goes 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then the next one flips every 2. So 0, 0, 1, 1. Then the next one flips every 4. And when it flips, so it flips every 1 and then stays on for half that time. So you could say like this is a cycle, right? 0, 1's a cycle, 0, 1's a cycle. Same thing here. This 0, 0, 1, 1 is a cycle. It will keep happening, right? So 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Next bit, 8 bits is a cycle, right? So 0, 0, 0, 0, 1, 1, 1, 1, and so on. So you could say for a given bit, like let's say we have the 0 bit. If we have, and I'm going to start with a 0. I'm going to start with a 0. So let's say we're figuring out like how many, just to keep it simple, how many 1 bits does every number from 0 to 10 have? So we know that every 2 numbers have one 1 bit for sure, right? Every 2 numbers have one 1 bit because it's a cycle. So we can say, okay, so 0 to 10, that's 11 numbers. So if we have 11 numbers and every 2 gives us a cycle, we can just do this, and we'll say we have 5 1 bits. Now we have a remainder of 1 number, right? Because there are 5 cycles, but then there's 1 more number. And now notice that in every cycle, the first half of the cycle is zeros, and then the next half of the cycle is ones. So for example, in this cycle, the first half is zeros, the second cycle is ones. In the cycle 0, 0, 1, 1, the first half is zeros, the next one's ones. Then in this next one, the first 4 is zeros, and the next one is ones, and so on. So we could say for a cycle of length x, first half is zeros, second half is ones. So we know for sure if we have complete cycles, we can basically break this down into complete cycles and extra. And so for complete cycles, our number of ones. So for complete cycles, let's see here, our number of ones equals the length of cycle over 2 times number of cycles. So let's make this a little bigger. Okay, times number cycles, right? Because half the cycle is going to be ones. We know it's like all a bunch of zeros and a bunch of ones. So for complete cycles, we can just say the number of ones is the length of the cycle over 2 times the number of cycles. Because half the cycle is ones, and then for every cycle, half of it's ones. Now for the extra, we know that the second half of the cycle is ones. So how many ones do we have? Well, it's just going to be the extra. So it's going to be the extra like whatever we have left, right? Extra cycles or something minus half of a cycle, or like length of cycle over 2. And obviously this will be like, if it's negative, then obviously it'll just be 0. But essentially, if we know our cycle is like 0, 0, 0, 0, 1, 1, 1, 1, and we have 3 extra cycles, not complete. So I guess this wouldn't be extra cycles. This would be like extra bits or something. And we have like 3 extra bits here. Then we know that those 3 are going to be 0. But if we had like 5, then we would do 5 minus 4, and we'd have 1. So hopefully that makes sense. You calculate how many total cycles you have, and you know how many ones you have there for each bit. It's just based on like what bit you're on. Each bit will have like the cycle length will double. Like I said, this is like 2, this is 4, this is 8, 16, and so on. So you calculate the number of complete cycles, and then the extra you just say like, if I have more than half the cycle, everything over half will be more ones. And then basically you can do this for every single bit. So you do this for every single bit, and you can basically just do a loop. So let's say you're looking for like bits for numbers less than 10. We can just start at like the 0 bit, and then we can go to the 1 bit, and then we can go to the 2 bit, and then we can stop at when our bit becomes bigger than the actual number. So for example, if we're looking for this bit, we know this won't exist because this is 16, right? So we can just do that. So hopefully that makes sense. I'll show you in the code, but that'll essentially give you how many ones you have. Now we need one more thing, and this is very similar. So we can calculate how many ones we have. But now how do we get this product? So this product is also very similar to how many ones we have with like a small change. So let's get rid of this, and let's go back to our picture. So let's say we want the product of 1 through 10 again. So basically for every single one, we can kind of reuse most of the logic for this first thing. But now we just have to think about like, for all these bits, first of all, we have to recognize that these are all powers of 2, right? So if we know how many 2's there are, for example, 4 is just 2 times 2, right? So that's 2 2's. 8 is 2 times 2 times 2. So that's 3 2's and so on. So if we can actually just figure out how many 2's total we have, we can just 2 to the total 2's. So for example, in this whole array would have like, so ones wouldn't count because 1's 2 to 0. So we'd have like 1, 2, another 1, so that's 2. Then 4 is 2 more. So 4, 6, 7, 8, 9, 10, 11, 12. And then 8 is 3. So we'd have 15 2's. And then we can just do 2 to the 15th. So basically we're going to be doing the same kind of thing, this counting bits. But now all we have to know is how much our 2 is worth. So for every bit we find, or for every number of bits we find, like let's say we're on number of like 2 to the 0 bits. Obviously, it doesn't matter how many we find here. These are all irrelevant, right? Because this is just 1. So like 1 times whatever doesn't matter. Like, right? It doesn't matter how many 1's we have in our big nums. It's not going to change anything. But if we count 2 to the 1 bits, so all of these here, then we know those are all worth 1, 2. So we're going to do the cycles and the extra and same kind of thing. So we'll calculate 5 here, and we're going to say, okay, we have 5 of these, and these are all worth 1 each. And now in our next one, we'll calculate 1, 2, 3, 4, 4, and they are all worth 2 each. And then in our next one, we'll have 1, 2, 3, and they're all worth 3 each. And the way to do that is just basically like what bit are you on? So are you on the 0 bit, the 1 bit, the 2 bit, and so on. So it's very similar with number of ones, except now you just figure out like what that bit is worth, and all the rest is the same. So in this case, we're going to have 5 plus 4 times 2 plus, actually, did I do that right? Oh yeah, 5 plus 4 is 2 plus 3 times 3. So here we have 8 plus 9, so 17, and 20. So we have 22 twos. And then basically at the end we can just do 2 to the 22, and that will give us this thing. And you can double check, maybe I did the math wrong. Or actually, definitely, so this 0 to 10 is not the same as this, right? This is like 0 to 7 or something. But 0 to 7 you can kind of do the same thing. But that's kind of how you could do it. So you separate it out into count 1s and count 2s. And once you do that, then you're basically done with the query. So you basically just say like, okay, give me the biggest number that fits in my query, and how many 2s are there in that number? Like, and what I mean is not the biggest number, but it would be like for 6, for example, that means 1 through 6 fit in my query, right? All the binary for all these fit in my query. And then also for my remainder, how many 1s are there, and what are the powers of 2s of that as well? And that you can just calculate separately, and then you just do both queries, and then you subtract one from the other. So let's say we have a query of like, let's say 10, 20 with some mod. That part doesn't matter. We can basically just say, okay, let's do 0 to 9. How many? And then let's do that, and then let's do 0 to 20. And let's say this gave us 10 twos. Obviously this is wrong, but let's say this gave us like 50 twos. Then we can basically say, okay, so in this midsection we just have 50 minus 10, so we have 40 twos, which means we just need to do 2 to the 40 modded by the mod value that they gave us. And that's basically it. So let's take a look at the code now, and it's going to make a lot more sense with that, hopefully. So essentially this is very similar. I could have made this like cleaner, but it's like not that bad. So we count how many 1s we have given our guess. And so we start at 2 to the 0, and then we just keep going until our power of 2 is greater than the number. And so we basically, this is the complete groups. So the complete groups is, and the reason I did num plus 1 is because if num is like if I go back to this picture, so the easiest way to do groups, like if num is 1, I want to count 0 as like part of my groups, because like this is a group. But if I do 1, it won't do the whole thing. So that's why I did num plus 1, because it did include the 0. So if like 6, then we'd have 7 total numbers to look from. So essentially the total numbers is num plus 1, and then the length of a group is start times 2. So for example, if start is 1, that means the length of a group is 2. So how many total groups do I have? And then the number of 1s in my group is just the bit that I'm on. So if I'm on 1, that means I'll have 1 1 in 2 groups. If I'm on 2, I'll have 2 1s in a group, right? So if I'm on this first bit, I'll have 1 in each group. Here I'll have 2 in each group. Here I'll have 4 in each group, and so on and so on and so on. So you get the total groups, then you calculate how much extra you have, and then you just say like, okay, if I have more extra than half of a group, then I'll add that, and then I'll go to the next number. Then the count 2s is very similar. The only thing I added was what's a 2 worth. And a 2 is worth either, 0, 1, 2, 3, and so on. And so it's this power thing where it's worth, like the first one is worth 0, then the second one's worth 1, then it's worth 2, then it's worth 3, and so on and so on. And then this basically just calculates how many 2s you have. Then we have a query function. So if there is some cases where I just didn't bother checking for, where if your query is like 0 to 10 with a mod, I didn't want to do, basically what I would do here is this would be like 0 to -1, and I just said like I don't want that. So if this is -1 or something, then just return 0. And so here, same kind of thing. I add 1 to the number just because the same kind of thing. Because basically, if I'm looking for, or actually, this was a different logic. So if I'm looking for like 10. I'm looking for 0 to 10, which is actually 11 numbers. That's why I added 1, because the length of the array is actually 1 more than that. And then we just binary search for the result in the extra, and we say, okay, give me the number of 1s that my current guess has. If my current number of 1s fits, then make the result that, and make the extra whatever extra I have, and then let's try a bigger number. And if it doesn't fit, let's try a smaller number. And then let's get the number of 2s for my result. And then if I have any extra, I can just calculate that from, I know exactly what number to look for, because like if 6 was the biggest number that fit, then I'd have to say, okay, well, I know that I'd have to look for how many 1s are there in 7, and I know how many to look for, so I just take the ones that are worth the least, and I keep going upward. And then finally at the end, you just return the query thing. So you can use a Python power, so it's just 2 to the number of 2s modded by mod. And it works. And yeah, I think this took me quite a while, probably like an hour or 2 at least. This is definitely like the hardest problem in a while, just to like figure out what's going on and stuff. But I did do problems, like not all these things, but I did do problems in the past where you did have to figure out like the number of 1 bits and stuff like that. So hopefully that is something you can reuse in the future, where you have these complete cycles and the extra bits. This is like a recurring pattern. I think I've done it 3 or 4 times. This is actually like this part in itself is like some easy problem, but this is like the optimal solution to some easy problem. I forget exactly which one it is. Maybe I'll find it later. But essentially this pattern of like groups of 2, groups of 4, groups of 8. But hopefully if you haven't seen it, you can use it now in the future. And yeah, so let's go through the runtime for all this stuff as well. So for this one, so essentially you'd have to do, for each query, you basically have to do a count 1s and count 2s. So count 1s for a number is going to be log of that number, because to go through all the bits of a number is logarithmic. Yeah, so it's going to be log of that number. And now the number can't, like, I guess the number can't be like too big, but I had it start with like the length of the query. So maybe like realistically it will never be like as big as this query's I. I think it'll be significantly smaller, but whatever. So that'll be that. And then let's see. And then you also have to do count 2s, which is like the same exact thing. So this is like log and another log. Now the binary search is another log. So I think it'll be something like for every query. So let's call this like number of queries. For every query, you have to do like log squared of like the biggest item you can have. So maybe we'll call that like M or something. I don't know. So I think it's something like that, because binary search is log, and then in every binary search you do these count 1s and count 2s, which is also another log. So it's like a log. Yeah, I think this actually can get factored out, so it actually actually maybe not. There's some like weird log stuff that I don't remember. And then space. Is this ov1? I think we don't have like anything extra. We just have like variables. So yeah, I think this is just ov1. Maybe I've missed something, but yeah. And then the other ones. So this dp is ov(n) squared, because we basically just have an index, which is ov(n), and then a loop, which is another ov(n). We have a letter count, which doesn't matter because it's only 26 letters, and then space is O of n. And then let's see. So this is n log n. Yeah. N log n, and then we have a visited set, which, let's see. Well, actually, I mean, we made this new thing anyway, so this is just O of n space, even if we don't care about the visited set, because we still use this. Yeah. And then the last one is, so this is just n by m, or whatever it is. Yeah, n by m. And space O1. And yeah, hopefully this is helpful. Definitely one of the harder contests for the last problem. Like, it'd be pretty nuts to get this problem during the contest. The rest of them, though, are definitely... And that's what I've been seeing recently, is almost all the contests, I can do the first 3 problems relatively quickly. And then the 4th one's kind of hit or miss. A lot of them are significantly easier than others. So maybe I'd do like 50% of them relatively easily. And then the other 25, like maybe 25% of the rest, pretty tough. And then 25% of like the last 25% is pretty nuts. Like this one is like, I'd say pretty nuts. But there's like for example, the other 7-point problem from the weekly contest was like okay, and there's a bunch of 7-point problems that are reasonably easy. So I think maybe just like the rating for these problems isn't like extremely accurate, I'd say, or maybe I'm worse at some things than others. So who knows? But yeah, that's gonna be all for this one. If it was helpful, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.